section is entitled Complex Numbers. A complex number can always be written in this form. Let A and B be any real numbers, including the number 0. Then A plus BI is a complex number. It's a real number plus a real number times I. This is called the real part, and this here is called the imaginary part. Let me give you some complex numbers, and I'm going to ask you to find the real and the imaginary parts. Right now, 13 is the last one, and the next one will be the last one, negative 8i. The last one is not 13 minus 8i. I just ran out of space on my board. This is one problem. This is the second problem. This is the third problem. The number 13 alone is the fourth problem. And negative 8i is the fifth problem. 7 plus 3i. Very simple. That's the real part. And this is the imaginary part. In the next one, negative 2 plus 3i. Very simple. That's the real part. And here is our imaginary part. The next problem is 13 minus 2i. That's the real part. And this here is the imaginary part. Actually, before we do 13 and negative 8i, how about we have 4i minus 7? How about we do that one first? 4i minus 7. What's the real and the imaginary part? If we can get it in our standard form, a real number plus a real number or times I, or minus a real number times I, will be in business. 4i minus 7 is the same as negative 7 plus 4i. But now with routine, here is my real part, and here is my imaginary part. Now if we can do the same with 13, we'll be okay. 13 is some number plus or maybe minus some number times I. Well, 13 is 13 plus 0 i's. So, the real part is 13, and plus 0i is the imaginary part. Okay, well, what if you just given what's called a purely imaginary number? 13 is a pure real number. Well, I like to write negative 8i as some number plus or minus some number times I. Well, we want to take away 8i and we want to have 0. 0 minus 8i is negative 8i. The real part is 0, and the imaginary part, including the sign, is negative 8i. Negative 8i is the imaginary part. Okay, same. In a moment, we're going to continue with the same question. Find the real and imaginary part. First, we need to review for a moment. If you have the square root of a negative number, the negative comes out as I. That is the square root of negative 3. This is kind of side work. Is I square root of 3. The square root of negative 16. The negative is I times the square root of 16. But I know the square root of 16 is 4. I times 4 is the same as 4 times I. So if I were to give you the square root of 2 plus the square root of negative 7, and I said write this in, what's the real part and what's the imaginary part? Well, you should say this is the square root of 2 plus the square root of 7i. That's the real part, and that's the imaginary part. I give you a fraction, negative 2/3. Don't be afraid of that. That's negative 2/3 plus no i's. That's your real part. In fact, it's a pure real number. A real number. Plus no i's. The imaginary part. Your imaginary part is 0. Okay, so I'm going to give you complex numbers, and I'm going to add and subtract them. You add the real parts, and you add the imaginary parts, and you're done. You subtract them, subtract your real parts, and subtract their imaginary parts. We're adding two such numbers. You can think of I as x. You can think 3 minus 4x plus 8 plus 6x, and you can say 3 plus 8 is 11, and if you take away 3x and you add 6 x's, you have 2 x's. But x is really I. You add those. 3 plus 8 is 11. So part of the answer is 11. You add those. Negative 4i plus positive 6i. That's 2i. So the final answer is 11 plus 2i. And of course, we wrote it in A, in this case, plus BI form. BI. When they say write in A plus BI form, I disagree with that. It should be A plus or minus. It only turned out that we had ended up with 2i. We could have ended up with negative 2i. So when they say A plus BI form, that means A plus or minus BI. A plus BI or A minus BI is acceptable. For example, if you have negative 3 minus 7i, and you add 5 plus 4i. Well, we're adding. You add those numbers. 3 plus 5 is 8. So we get 8. And you add those numbers. Negative 7 plus that plus 4. 4i's. It's negative 3. Negative 3y, negative 3i's. If I multiply by all the numbers that I just added by I, then my answer gets multiplied by I. Okay. Now, this is that's minus bi. If they, in my opinion, and there's no question about it, if they wanted in a plus bi form, remember that it's understood to be plus 3i. You have every right to change both of them. Why would you want to? Because you want a plus in the middle. A plus negative 3 is bi. That's in the form a plus bi. 8 minus 3i is not. That might be a. That might be b, and that might be I. But that's a minus. So when they say a plus bi form, that means a plus bi or a minus bi. So in the end, there's the answer. Notice, it wasn't because the negative 3 and the 5 were first that I combined them, in this case via addition, but I did that first because in my answer, I first want the real part. A is the real part, plus bi, or minus bi. There's their minus bi. The last part, the bi should be at the end. That's why I wrote the 8 first. What if you had 5 times 2 minus 3i, or maybe 3 times 2i plus 4? Write this in a plus bi form. Well, the first one, pretty routine. 5 times 2 is just a whole number, which is good, because we want the first part to be whole. 5 times negative 3i is negative 15i. And there's my answer. A minus bi. The next one, if I need to multiply 3 times the 2i, and at some point 3 times 4. The order I do this in is up to me. I meant to say times by plus 4. The order I do this is up to me. I want to get the real part first. So I'm going to multiply 3 by 4 first, which is, or 3 times positive 4, which is 12. And now I'll do 3 times 2i, which is positive 6i. It's up to you which way you multiply. You've all been taught that you do a times b and then a times c, but you don't have to. After all, you did also learn that b plus c is c plus b. That is, you can multiply using your rule that you have to multiply the first thing by a first and then the second thing by a second. Good, I agree. I have to multiply a by c first and then a by b. In this case, if you have to multiply what's in the brackets by left to right, if that's what you think, well then first you have to multiply by b and then by c. And in this case, it reversed. First you're multiplying by c, and then you multiply them by b. It reversed, but they're equal. You can do, in the first box, you can do a times c first. You can do a times c, and then do ab. I know you can, because that's what it tells me here to do. ac plus ab. Okay, think about that. Okay, now, what if we multiply complex numbers? Just remember that I squared. I is the square root of negative 1. So I squared will be the square root of negative 1 squared. You have the square root of anything, and you multiply it by the square root of the same thing. You get that thing. You get what's underneath the square root sign. So I squared is negative 1. So when you multiply complex numbers, up with one exception, you should treat the I as like it was x. Okay, treat the I like it was x. And let's make that something different. Let's make it a 7. The 5 is a 7. Alright, so we multiply like normal. Instead of having the normal or the typical variable being x or y or z, right now it's I. 3 times 2 is 6. 3 times positive 7i is 21i. Negative 5i times 2 is negative 10i. Well, I'll put those under the other i's. And negative 5i times positive 7i, well, negative times positive is negative. 5 times 7 is 35. I times I squared. Okay. Adding this, we get 2 plus 11 i's minus 35 r squared. But I squared is negative 1. I squared is negative 1. So it says at the very, very top. I squared, negative 1. Okay, so what we have is 2 plus 11i, negative 35 times negative 1, plus 35. More like terms. 2 plus 35, they're like. 37 plus 11 i's. So with the exception of saying that I squared is negative 1, it was just like I being x or y or k. Let's try another one. Do one more multiplication. Then we'll talk about division. We have negative 2i plus 3 times 11 minus 13i. So you multiply. Negative 2 times an understood positive 11. That's negative 22i. You multiply that. Negative times negative is plus. 2 times 13 is 26. I times I, so I squared. Plus 33 minus 39i. So this minus that is going to be minus 61i. Minus 61i. And this will be negative 26. Because positive 26 times negative 1, I squared is negative 1, is negative 26. So we added those two. That gave us negative 61i. This piece we just dealt with, it's negative 26, and this term is plus 33. Negative 26 plus 33, or 33 minus 26, is 7. I wrote that down first because it was real. Minus 61i. Okay, now multiplying complex numbers, dividing complex numbers is a whole nother case. Notice that a complex number is in the form a plus b times I. If you take that complex number and multiply by what's called its complex conjugate, the complex conjugate of this number is that number. Notice only a sign change in the middle. The complex conjugate of this number is that number. That is, they're both complex conjugates of one another. Let's see what happens when you multiply complex conjugates. Well, you get a times a, which is a squared. You get a times negative bi, which is negative a bi. You get positive bi times a, which is the same as bi times a. That is, it's the same as a times bi. And then positive bi times negative bi. Positive times negative is negative. B times b is b squared. I times I is I squared. Well, if you take away ABI and then you add back ABI, it's as if there were no ABIs. So we're left with a squared minus b squared I squared. The I squared is negative 1. And negative b squared times negative 1. Negative times negative is positive b squared. If you multiply complex conjugates, if you take a plus bi and you multiply it by a minus bi, you get a squared plus b squared, which, by the way, is a real number. This is very important. It's a real number. Just remember, a was a real number, you square it, it's real. B is a real number, you square it, it's real. You add up two real numbers, you get a real number. This is very important theorem here. It makes life rather easy. If you take a and b and you square them and add them up, you have the answer. This here says to square a and square b and add them up. That's what you do when you multiply complex conjugates. If you have 3 plus 4i and you multiply it by its conjugate, 3 minus 4i, you will get 3 squared plus 4 squared. You don't want to look there, you can look here. 3 squared plus 4 squared. You want to look at both of them, you get 3 squared plus 4 squared. And if you remember Pythagorean's triples, 3 squared plus 4 squared is 5 squared, or 25. 9 plus 16 is 25. Notice I didn't FOIL out. I FOIL out one time and one time only. Here it is. There it is. Do it once yourself so you can say you did it too. And then never do it again. If you multiply complex conjugates, you square those two numbers and then you add them up. That is, if you have 5 minus 3i, the complex conjugate will be 5 plus 3i. You get 5 squared plus 3 squared. I think that's 34. 25 plus 9, 34. You get a real number. Sometimes you get 25, a real number. You always get a real number. You always get a real number, and you don't have to FOIL out. Because we know this theorem that's left on the board. This theorem here. Okay, if you have negative 2 minus 3i, the complex conjugate will be negative 2 plus 3i. And the answer will be 2 squared plus 3 squared, which is 13. 2 squared is 4, 3 squared is 9, 4 plus 9, 13. Anytime you have a number in the form a plus bi, it's easy to find the conjugate. It'll be a minus bi. Anytime you have a number in the form a minus bi, it's easy to find the complex conjugate. It's a plus bi. So, if I give you negative 4i, what would the complex conjugate be? Well, write it in a minus bi form. Realize you can always have 0. That's a plus bi form. The complex conjugate will be 0 plus 4i, which is 4i. So negative 4i and positive 4i are complex conjugates. So when you multiply them, you better get a real number. Well, one way to do it is to look at it from here. If you multiply those two numbers, you get 0 squared plus 4 squared, which is 16. On the other hand, if you did negative 4i times positive 4i, well, negative 4 times positive 4 is negative 16, and I times I squared, which is negative 1, well, that too gives us the same 16 as a moment ago. So if you have a pure imaginary number, you can still write the complex conjugate. The complex conjugate of plus 8i, or just 8i, we'll think of it as 0 plus 8i. And the conjugate, complex conjugate, will be 0 minus 8i, or negative 8i. If one number is plus 8i, the complex conjugate will be negative 8i. So sometimes you'll have to find the complex conjugate of just a pure complex number. When might you want to find complex conjugates? And the answer is when you divide complex numbers. Final answers should never have complex numbers in the denominator. Final answers should usually be written in a plus bi form. So if you have 7 plus 2i, and you're dividing this by 3 plus 4i, and you're asked to write this in standard form, a plus bi form, well, we want to change the way this looks then. If you want to change the way something looks, you take that something, and I just did, I wrote it down, and you multiply it by 1. You can always multiply by 1. If you want to change the way something looks, you multiply by 1. And in this case, I want the bottom to be 3 minus 4i. Because when I multiply those bottoms, I'm going to get 3 squared plus 4 squared, and that doesn't have any i's in it. Now, if what's in this bracket has any chances of equaling 1, then the top has to be exactly the same as the bottom. Be exactly the same. Okay, now we have to just clean up the top. 7 times 3 is 21. 7 times negative 4i is negative 28i. Plus 2i times 3 is plus 6i. And positive 2i times negative 4i is negative 8i squared. 3 squared plus 4 squared is 9 plus 16, or 25. And for the real number, remember this is negative 8 times negative 1, which is positive 8. This is negative 8 times negative 1, which is positive 8. 21 plus 8 is 29. And if you take away 28 i's and you add back 6 i's, you've only taken away 22 i's. Now this is not an a plus or a minus bi form, but this is 29 over 25 minus 22 over 25i. And I guess you should check to see whether or not you can reduce that. And in this case, you can. So multiplying by complex conjugates got their denominator to not be complex. You had 2 minus 3i, and you want to divide this by 1 take away 2i. You want to clean this up. You want to write it in a plus or minus bi form, standard form. That is, we want to change the way it looks. You want to change the way something looks, multiply it by 1. Since we want to play games with the denominator, we want it to become a real number, I should multiply by the complex conjugate. Now that's what I do on the bottom, that's what I have to do on the top. Within these brackets, it's 1. So for the bottom, it's routine. It's 1 squared plus 2 squared. I think that's 5. 1 plus 4. That sounds like 5 to me. Okay, let's figure out what the numerator is. 2 times 1, 2. 2 times positive 2i is positive 4i. 3i times 1, negative 3i times 1, excuse me, is negative 3i. And negative 3i times positive 2i, well, negative times positive is negative. 3 times 2 is 6. I times I is I squared. But just remember, it's not negative 6, it's plus 6. Because if you multiply negative 6 by I squared, that is by negative 1, the sign changes. When you multiply by negative 1, the sign changes. So if you have every number, like 8, which is understood to be plus 8, if you multiply it by negative 1, you get negative 8. If you started off with negative 16 and you multiply by I squared, you get back positive 16. Okay, 22. I'm back at the numerator. 2 plus 6, 8. 2 plus 6 is 8. That 2 and that plus 6 is 8. And then in the middle, positive 4i minus 3i is positive 1i. The final answer is 8 over 5 plus 1 over 5i. A plus bi form. There's no way, this may be the wrong answer, but there's no way that's not an A plus bi form. No way about it. The next thing we're going to talk about is I to various integers, positive integers. I'll show you the y's, and then I'll show you how you can just mechanically do it. You must know this. Any number, including I, to the 0 power is 1. Anything to the first power is that anything. I squared is negative 1. Because I is the square root of negative 1, you square it, you get back what's underneath the square root sign. I cubed is really I squared times I. But looking right here, I squared is negative 1 times I is negative I. It's negative I. I cubed is negative I. And I to the 4th, well, that's an easy one. I to the 4th is I squared times I squared. Negative 1 times negative 1. Negative 1 times negative 1 is positive 1. So those are, excuse me, we didn't even need the last one. These are the 4 that we should know. We didn't need to do the last one. It was correct, I to the fourth is negative 1, but we didn't need it. Just like I didn't write down I to the 6, or I to the 7, or I to the 5. These 4 you have to know. You must know these 4. Now, if I ask you what I to the 97 is, what you do is you divide by 4. You always divide the power by 4. 4 goes in here 2 times 16 with 1 left over. Remainder 1. This is equal to I to the 1, and then I look at my cheat notes here and I get that it's I. We'll come back and see the y's in a moment. If somebody asks you what I to the 26th is, you do 4 into 26, go 6 times, that's 24, 2 left over, the remainder is 2. This is equal to I squared, and I squared is negative 1. You must know those 4. If I give you I to the 100, well, if you do 4 into 100, it goes 25 times and remains a 0. So it's I to the 0. It's always I to the remainder, but that's 1. So I to the 100 equals 1. Just divide by 4. Okay, if you have I to the 19, you do 4 into 19, goes 4 times, used up 16, 3 remainder. The remainder is 3. So I to the 19 is I cubed. But I cubed is negative I. You must know those 4 in the top left. You must know those 4. At least be able to figure it out. Now, why is this working? Let's look at I to the 97. Let's look at 97. If 4 into 97 is 24, remainder 1. That means 97 is 4 times 27. That used up 4 times 24. That used up the 96 plus 1 more. That is, this is I to the 4 times 24 plus 1. Now remember, a to some power times a to another power, well, that's a to the a plus b power. A plus b. That is, if you have a base and the power is an addition, you can write it like this. That is, here's my addition right there. It's I to the 4 times 24 times I to the 1. Okay. Notice that that's always going to be the remainder, because that's where the plus sign's coming from. For example, 26. 26 is 4 times 6, 24, plus 2 left over. That is I to the 26 is I to the 24, 4 times 6 is 24, times I squared. Okay, now, what happens, what is happening? 4 times 24 is the power. That's the same as I to the 4th raised to the 24th power times I to the 1 in this case. But here's where dividing by 4 doesn't change anything. I to the 4th is 1. 1 to the 24th is 1. 1 times I to the 1 is I to the 1, which is I. The answer is I. Okay. The answer is simply I. Divide by 4 and find the remainder. And the answer is going to be I to the remainder. Remember, when you divide by 4, the remainder has to be below 4. Either 0, 1, 2, or 3. That is why we must know that table in the left corner. We must know that. Or at least be able to come up with it. Let me show you again how you can come up with it without even remembering it. Few rules. Anything to the 0 is 1. Anything to the 1 is the anything, in this case I. And most students tend to remember I squared is negative 1. Remember, if you multiply I to the 1 by I squared, you get I cubed, which is the same as multiplying those two, which is negative I. That's how you can remember it. One more example. Somebody asks you what I to 2007 is. You do 4 into 2007. I'm pretty sure the remainder will be 3. You take away 500, 2 4s, which is 2,000. You subtract, you get 007, which is 7. Oh, excuse me. You subtract those numbers, you get 0. You bring down the 0, which is just 0. 4 does go into 0. It goes in 0 times. 0 times 4 is 0. You subtract, you get 0. You bring down the next number, 0, which is 7. 0, 7 is 7. 4 goes into 7 one time. That used up 4. 3 are left over. That is, this is the same as I cubed, but I cubed is negative I. Just divide by 4 and find the remainder. All I care about is the remainder. The remainder goes to the power. You were taught, for example, the square root of 3 times the square root of 12 is the square root of 3 times 12, which happens to be the square root of 36, which is 6. That is, you were told that if A and B are positive, then the square root of A times the square root of B is the square root of AB. In fact, most books write this. But in fact, only one of the two have to be positive. Now, here's where it won't work if they're both negative. The square root of negative 3 times the square root of negative 12. Well, is this equal to the square root of negative 3 times 12, which is the square root of 36, which is 6? Well, let's see. The square root of negative 3 is I square root of 3. And the square root of negative 12 is I square root of 12. Because the minus sign comes out as I. Okay, so the square root of negative 3 times the square root of negative 12 is this times that. It's I square root of 3 times I square root of 12. Well, I times I is I squared, and square root of 3 times square root of 12, having done it already, we know that it's 36. It's 6. And if you want to write it as square root of 3 times 12, that's negative 1. Square root of 36 is negative 1 times 6. It's negative 6. They're not equal. They're not equal, which means bye-bye equal sign. Bye-bye. It's not there. It's not there. the square root of a negative number times the square root of that negative number is not the square root of the product of the two negative numbers. Can one of the numbers be negative only? And the answer is, of course. That's what we've been doing. That's what we've been doing. Why do you think the minus sign, that minus sign, comes out as I? The reason is, this is negative 3 is the same as negative 1 times 3, which is the square root of negative 1 times the square root of 3, but the square root of negative 1 is I square root of 3. But that's pretty much what I'm saying. The minus sign comes out as I, and you would get I square root of 3. And we definitely just showed a case where if you have a square root under the radical and a square root of two numbers, and under the radical you have a product of two numbers. If exactly one of them is negative, you could split them up. Now you may say, well, what if I have negative 2 times 4? That's not a 1. Well, sure it is. Here's the 1. This here is negative 8. That's the same as negative 1 times 8. So you get I square root of 8. You get the square root of negative 1, which is I, times the square root of 8, which is square root of 8. Okay? Which meant you could have, from the very beginning, say it's the square root of negative 2 times the square root of 4, because the square root of negative 2 is I square root of 2, times square root of 4 is I square root of 8. And we can simplify this. Square root of 4, square root of 8, square root of 4, times square root of 2. That will be 2i. Square root of 4 is 2. I times 2 is the same as 2 times I times the square root of 2. So, if you have two negative numbers being multiplied underneath the square root sign, you cannot separate them. If one or none are negative, you can break them up. If you have two under, you have the square root of a negative number times the square root of another negative number, that is not the square root of the product. Okay, so how about we graph some complex numbers? Graph these complex numbers. Now, graphing complex numbers, very, very simple. Along the horizontal axis, you put the real part, and along the vertical axis, you put the imaginary part. For example, this point right here would be 4 minus 3i. Because the real part is 4, and the imaginary part is negative 3. It would be 4 plus 3i. 1, 2, 3, 4, 5. 5 minus 2i, or minus 4i. Minus 1, minus 2, minus 3, minus 4. This point will be 5 minus 4i for one reason. The real part is 5, and when I look across, that's what I see. And the imaginary part, minus 4i, well, how many i's is that? Minus 4. So when you look down, you should see minus 4. That's how you plot complex numbers. So if you were asked to plot the square root of 3 plus I, well, square root of 3. what's the smallest number above 3 that you know the square root of? And the answer is 4. You know the square root of 4. 2. What's the largest number below 3 that you know the square root of? Well, below 3. 3, 2, 1. You know the square root of 2? No. You know the square root of 1? Yes. Square root of 1 is 1. I want the square root of the first number above 3 that I know the square root of? 3. 4. You know the square root of 4? Yes. For example, somebody gave me the square root of 7 and said, what's it in between? I would go 7. Do I know the square root of 8? No. Do I know the square root of 9? Yes. Which is 3. That is, the square root of 7 is below 3. Now, I start at 7 and I go down. Do I know the square root of 6? No. Do I know the square root of 5? No. Do I know the square root of 4? Yes. It's 2. The square root of 7 is in between 2 and 3. So I did this just to show the bottom left. I did that just to show the square root of 3 is between 1 and 2. So I go to square root of 3. Say it's right there. Square root of 3. And it's understood that the imaginary part is plus 1i. Plus 1i is here. And I go to where they intersect. Right here. Right here. That point is square root of 3 plus I. Because at that point, if I go to the x-axis, not far, far away, I see square root of 3. Right there, square root of 3. And if I look to my left, I see 1. Square root of 5, square root of 3 plus I. Okay, that finishes up complex numbers.